Hi everyone, welcome to our Diabetes Health Indicators Insights final presentation. I am Zach.
I'm Gideon. So for this assignment, we used the dataset from the BRFS survey, which is the Behavioral Risk Factor Surveillance System that was collected in 2015 by the CDC. This is a survey that goes out to hundreds of thousands of people each year. And this specific dataset has around 253,000 rows in it. Well, the actual survey is more expansive. This has 22 features from it. And specifically, we were looking at a large number of binary features, such as high cholesterol, whether someone smokes, whether someone's physically active, as well as some multi-categorical features and numerical features, such as income category, BMI, age group, and physical and mental health scores. Our objective for this was to try to classify whether someone had or did not have diabetes with the less than 5% type 1 error and hopefully an around 1% type 2 error. However, we weren't able to achieve this. Our best results had multiple times this error. We were able to achieve significantly better than a simple linear or tree classifier. Our second goal was to try to identify some correlations in order to give advice on how to prevent diabetes.
So for our initial exploration, we started by looking at the correlations between the different factors and whether or not someone has diabetes. We found that the main correlating factors included high blood pressure, high cholesterol, BMI, heart disease and attack presence, general health, physical health, difficulty walking, and age. Other feature correlations were less specific, each having an absolute value of less than 0.1, as shown in the correlation table in Figure 1. Overall, however, none of the correlations are particularly strong. The highest, physical health, only had a correlation of about 0.3. We then attempted to explore some naive linear PCA coupled with clustering techniques to explore the shape and feature distribution overall of our dataset. We attempted to find identifiable clusters by performing k-means on the dataset and used the Kalinske-Horobatz score heuristic for each k number of means to determine the optimal value. The result of this analysis is shown on the slide, which led us to use k equals 3. We then applied this naive PCA to our dataset and created a scatter plot on the top two components. We colored this both with the k-means result and the diabetes status of the individual. Interestingly, this showed better separation, but still with a significant amount of projective overlap between diabetes and non-diabetes points. And these results both indicate that the dataset overall is quite noisy in terms of our target quantity, diabetes presence, and exhibits large amounts of variation in terms of our feature distribution. We then explored kernel PCA using scikit-learn implementation, and while this did show some promise at creating clusters, the groupings were ultimately unhelpful at differentiating between the diabetes cases.
So we started our classification attempts with decision trees and random forests because we recognized that the boundary was nonlinear and we didn't expect any linear methods to perform well. So we started out with some simple and hybrid trees, but we weren't able to achieve anywhere close to our goals. And the trees also struggled with prioritizing type 2 error over type 1 error, as can be seen here. So for random forests, we tried using Gini splitting as a standard, but that again had the same difficulties despite having slightly better performance. To try to avoid this, we tried weighting the diabetes class higher than the non-diabetes class for the purpose of training the forests, which did result in some marginal improvements, but overall it did not improve our error ratio. And the fact that the trees were struggling can definitely be seen over here, where despite having only 22 features, our minimum depth was 32.
So these somewhat disappointing results suggested that a much more sensitive and tunable classifier framework was needed. So we tried employing dense neural networks under the Keras framework. And this time, however, we were able to control our classifier based on a confidence threshold, as our MLP output gave a sigmoid probability, analogous to an NP detector, allowing us to set an optimal confidence threshold. And in this case, however, the overall accuracy of about 86% on our 2/3 test data split, coupled with a maximum recall score of 0.55, left much to be desired in terms of our overall total error rates. And it suggested that an even more powerful and customizable classification framework was needed, which could also be better tuned for this purpose with fewer hyperparameters. Further investigations in a dense neural network architectures with standard cross-entropy losses and modified weighted cross-entropy losses were unsuccessful in reducing these error rates overall.
So as a state-of-the-art method, we employed gradient-boosted trees through both light GBM and XGBoost, and these let us construct classifiers with greater overall accuracies. So we started out with light GBM, and we were able to create a classifier with greater than 93% negative precision and 59% positive recall. This was still less than ideal for our goals, but it was still the best result that we saw so far. Specifically that improvement was with regards to the lower type 2 error rates, which was our primary goal here. So we then tried with XGBoost, where we did a grid search for the optimal threshold, similar to how we did with the dense network, and as would be done in a Neyman-Pearson classifier. Initially, we had achieved a type 1 error rate of about 20% and a type 2 error rate of 37%, which was not very good, but after settling on optimal values for the hyperparameters and the threshold, we were able to get a type 1 error of about 34% and a type 2 error of only 16%, which significantly improved our initial results.
So in order to make public health recommendations for reducing overall rates of diabetes, we wanted to identify the boundaries of our classifier and see if we can extract some characteristics of different groups at these boundaries. So given the highly nonlinear nature of the XGBoost tree classifier and the sparse nature of our data, we chose to use the data from our classifier instead of analytically. We then started by finding the set of points near our decision boundary of the classifier, and then performing k-means on the set, which represented those at risk of diabetes. And this gave us both reasonable points at which to find the boundary, and it also gave us a set of data points at each of these locations. And the hope was that by dividing this boundary up into different regions under k-means, each of those regions would be small enough to have an approximately linear boundary. So to visualize this clustering, we used kernel PCA, since linear PCA didn't give us enough of a visual separation for clarity, which made sense given that LDA struggled originally. We found that the first PCA component was quite unhelpful for distinguishing most of these groups. However, it showed a very large difference between cluster 12 and the rest of these clusters. And looking at the centroids, we found that this difference from cluster 12 was because it did not have their cholesterol levels checked within the last 5 years, whereas every other cluster did. So to find the features most responsible for differentiating between those with and without diabetes within each of these clusters, we applied LDA individually on them. While many of these clusters were not very separable under LDA, about a third showed at least some separation.
So the results of that LDA analysis can be seen here. Here's some histograms of the plots, and here is a example LDA vector normalized against the standard deviations. So we were able to find that overall, stroke, heavy alcohol consumption, and heart disease were among the very strong correlating factors in all of the at-risk groups. And so we also looked at a few specific groups. Among those with high BMI, which we found in cluster 3, with an average BMI of about 41, we were able to find that the strongest correlating factor for diabetes was a lack of access to healthcare, which was often due to the no doctor because cost field right here. We also looked at those who rated themselves as having poor physical and mental health in category 4, and we found that stroke and heavy alcohol consumption were among the top correlating factors for diabetes as well. Interestingly here, vegetable consumption featured strongly as a negative correlating factor. Lastly, we looked at cluster 12, which again is those who did not have their cholesterol levels checked, and we found that there, again, heart disease, heavy alcohol use, and high blood pressure were correlating factors. However, here we found that access to healthcare was a positive correlating factor for diabetes, which we expect is due to the fact that you cannot be diagnosed if you don't access healthcare. So overall, in our attempts for classification, we were not able to achieve the performance that we had hoped. We think that this is largely due to the noise and due to the number of Boolean categories in the dataset. This also made it difficult to find correlations for categories. And we think that we did a pretty decent job at this last part by looking specifically at the boundaries. For future work, we hope to use feature embedding as a way to improve our classifier's performance.